Ladies and gentlemen, welcome, and I would like to thank the organizer of this conference for inviting me. Through contacts and meetings, an array of asymmetrically substituted perylenediimide compounds, synthesized by different very good groups in the world, found their way to Amsterdam, where I was working again at my alma mater. So what you see here is, I would like to call it a molecular symphony. It is a symphony of asymmetrically substituted perylenebisimides compounds that were studied in Amsterdam in the last 4 years. So all these diverse structures have a common theme, a common goal, to control the photoinduced flow of energy and electrons in molecular architectures. Nature is our main source of inspiration. Nature has learned us that in the photosynthetic reaction units in plants and bacteria, beautiful self-organized arrays of multichromaphoric structures assembled in protein matrices convert the energy of photons into the energy that can be stored and used, with photoinduced energy and electron transfer as the first primary events. So to monitor the photoinduced flow of energy and electrons, we mainly use femtosecond absorption spectroscopy. This technique was developed by Lyle, and basically it makes use of the speed of light to change the overlapping time of two correlated laser pulses. So the trick is to make the pathway of one of the pulses longer than the other. Our results are explained in theoretical frameworks such as the electron transfer theory developed by Marcus, and the theory of energy transfer that was developed by Theodore Fuster. The building blocks that we apply are splendid chromophores that are photo and electroactive, as well as supramolecular building blocks. So, with the outcome of our research, we will not solve the problems related to the energy needs of our planets, but we can make a contribution to the development of photoelectric paints or maybe cheap organic solar cells. And as you can see here, some people have envisioned that long-range electron transfer could be used to gain energy. Okay, what I will do today is to tell you something about the things that we've been doing in Amsterdam, to give you a flavor, and the things we have been doing together with the groups of Professor Famagusta, unfortunately not here today, and the group of Triplet. So I will start with telling you something about these light harvesting diets, and they are interesting with regards to application of organic solar cells. So as you may know, fluorine atoms are the major component in an important class of organic solar cells, polymer solar cells. So in this covalent combination of two n-type molecular materials, we combine the spectral properties of the fullerenes with those of the perylenediimides. The fullerenes have rather special electron accepting properties, and due to their spherical shape, they can accept electrons from all sides. Also, they are characterized by a very low internal reionization energy, which is of course very important in electron transfer theory of Marcus. The reduction potentials are quite low, similar to quinones, the final electron acceptor in the natural photosynthetic reaction center. But they have a rather low molar absorption coefficient. So fullerenes do not absorb a lot of light. So people have of course also shown already that the C70 adapt, which absorbs more light, actually performs better in organic polymer solar cells. So perylenediimide, on the other hand, they have a very high molar extinction coefficient, and they are known for a very high luminescence quantum yields in general, and they are very photostable. They're also used as pigments in car paints. And the reduction potential is similar to that of the quinones and the fullerenes. So as you can see here, we have changed the substituents on the A, being either chloro or phenoxy, and the spatial limit is varied. So the fast spectroscopy of these compounds was performed by the Vietnamese student Van. And they were synthesized by Jérôme Lafaux in France. And what you see here is that this is the absorption spectrum of the C60 unit, so the line is down here. This is the absorption that is due to the perylene units. So you see that there's a huge change, of course, in molar absorption. And this is, of course, used for light harvesting. Now, if you take a look at the emission, then we see that the emission intensity is about as low as that of the fullerenes. This here is actually the emission of the fullerene unit. And this is has a quantum yield of about 10 to the minus 4. So the emission of the perylene is in the same order of magnitude. It is extremely quenched because most perylene compounds, they have a quantum yield of about 1. So what we see here is the femtosecond transabsorption spectrum. Actually, it's the 3D data matrix of this compound in toluene. So here we see the wavelength, here we see the time, and here we see the signal intensity in differential absorption. So this is like a fingerprint of the excited state of this molecule. And, well, we see quite a few features. So, of course, here in the beginning, we see that the signal is 0, is the baseline, is good. Then at time 0, we see actually the chirp and some Raman features. But then the real important signals start. So we see the negative signal, which is the ground state bleaching and the emission. And here we see the absorption of the single excited state of the perylenediimide. Okay, the ground state bleaching is basically related to the spectroscopy. So if you hit your sample with an intense laser pulse, all the molecules are in the excited state. Now, of course, it's differential absorption. So you get, if you again probe this area, you get a negative signal, which is the same shape as the absorption spectrum, and this is the ground state bleaching. So here we have the emission. Now, at a little bit later time, we see a rather broad signal, and at last we see the development of this band at around 560. So here I have actually shown the same data, but I have inserted in black the transabsorption spectrum of the fullerene reference compound. So that's the black line here. So you can see from this data that at around 80 picoseconds, the only excited state species that is present is the excited state of the fullerene. Now before that time, we see again this bleaching and emission and this absorption of the single excited state of the perylene, and we see that it decays very fast. Now on a longer time scale, we see the development of this band at 560, but we also see that this ground state bleaching, that it has increased again. So this indicates that this excited state that is formed on a long time scale, that is localized on the Perylenebisimides unit, because that is bleached. So in fact, that is a perylene triplet state that is formed. So from the global analysis and the kinetics, we find two rates of energy transfer, of single energy transfer, which we attribute to two conformations, a folded one and an extended one. So in the folded one, the energy transfer occurs on an 0.4 picosecond time scale. So here we have summarized the processes that are occurring in these systems. So we have a folded conformation and an extended one. We have very strong light absorption by the PDI dye and the perylene units. We have fast energy transfer to the singlet state. Of course, then we populate the singlet state of C60, and it intrinsically forms very efficient the triplet. So then, actually, we see energy transfer, triplet energy transfer back to the PDI unit, and we generate the triplet of the PDI in quite high yields. So, of the first part, we can conclude that we have very efficient light harvesting by the PDI dye, and very fast single energy transfer to the C60 units. The triplets is formed with quite high yields. And only in the lower systems we see some slower triplet energy transfer. If we compare the behavior of these molecules in different solvents, we don't see a big effect, so it indicates that there's no charge separation occurring. Now, as I showed you, the dynamics in the excited states indicates the presence of a folded and an extended conformation. Now, this relates to the non-equilibrating excited state rotor principle of Huri. And interestingly, with NMR, you cannot differentiate between these two conformations. So here is the NMR spectrum of one of the diodes. So we actually see that all these four hydrogens have a different, they behave differently. And we can simulate the spectrum with one set of data. So this indicates that the two conformations actually have the same NMR spectrum. So clearly, with our excited state spectroscopy, we are probing populations in the ground state. So, of course, since this is a general chemistry conference, now, if we take the perylene-diimide, we can react it with two similar amines, then we get a statistical mixture. Of course, after extensive chromatography, this compound can be isolated, and it was reacted with ethylmalonyl. And the last step is, of course, a Bingham type addition to the C60 unit. Now, I told you, these materials have been designed for organic solar cells. And we see in solution that there's a strong interaction between the perylene dye and the C60 unit, and there's very fast energy transfer. So the light harvesting works. But I can tell you that if we apply these types of materials in organic solar cells, similar to these, but then of course with the perylene dye, then we actually get 1% of efficiency. So that's not extremely good, because with PCBM and thiophene, you can get 5% these days. But of course, in our system, we do not have the formation of interpenetrating nanoscopic networks. That has been shown for these types of fullerene polymer solar cells, that this is a very important aspect. Now, of course, we have on our system, we have one of the IMID functions, which is still free. So we can incorporate on that side a supramolecular functionality with which we want to steer the formation of interpenetrating nanoscopic networks. But we have shown, of course, that the light absorption and the energy transfer, that it functions quite well. So the next topic that I would like to discuss is a collaboration with the group of Professor Famagusta. Unfortunately, not here, and it's the work of PhD student Huri Icil. Basically, it is glycerin-linked arrays of different types of perylene dyes, and it contains of perylene orange, perylene red, and perylene green. And here we see that we excite the system 490, which is basically selective excitation of the orange chromophore. And we get very fast cluster type energy transfer to the red perylene unit. And next, very fast energy transfer to the green unit, which then can emit all the light. So in the system we have some competing Photoinduced electron transfer. So this glycerin unit in combination with the orange chromophore gives some, let's say 10% of charge separation. And of course, here this one has the phenoxy groups in the bay position. And this one here, the green perylene, was introduced by Wassilewski. It has the perylene groups here on the bay position of the perylene units. So these compounds were synthesized by Katerina in about 3 years, and then she came 3 months to Amsterdam and did all the time zone spectroscopy. And here we see that these compounds absorb a whole nice range of the sunlight or of the light. They cover a large part of the solar spectrum, and we see that it is basically a sum of the absorption of separate chromophores. So here we see the orange, here we see the red, and here we see the green chromophore. And next to that, we can also see that there's a very good spectral overlap. And of course, spectral overlap is very important for first-type energy transfer. So here we see that the emission of the orange and the absorption of the red, that there's good overlap, and also of the emission of the red and the absorption of the green. So these are the two overlap intervals, which of course govern the first-type energy transfer. So with femtosecond spectroscopy, we've been able to monitor these processes. So similar to the things that I've told you on the C60PDI system, this is also signatures of different excited states. So we see the signature of the excited state of the orange chromophore converting to the signature of the red chromophore and then final to the green. So from analysis of this data, we can get the rates of so we can get information about the interaction between these chromophores. And of course, in the, let's say, the photosynthetic light harvesting system, there's also energy transfer on a similar time scale. So the combination of these types of chromophores could be used to harvest light. That's what we want to show. So currently, we're also looking at a system that incorporates pyrene as an electron donor, also Caylus linked. And from the femtosecond transient spectroscopy, it is grown actually in the visible, but also in the near infrared region. And we get information that there's actually two types of charge-separated states. So this signal here, at around 980, this is due to the random anion of the perylene unit. So we see that there's a sharp one and a more broad one. So we believe that there are two different types of excited states, of charge transfer states. And we attribute this to the formation of an extended state and a bi-stacked conformer. So again, we see from the dynamics in the excited state that there's two populations of these molecules. And okay, this is of course extending into light harvesting combined with electron transfer. So this is like a cartoon displaying these two conformations, the bi-stacked, where there's fast charge separation, and an extended one, which there's much slower charge separation. So we can differentiate between these. And as a last example, we've been working together with people in Eindhoven, and this is on an electron acceptor system consisting of an oligo-phenylene unit. So this here is the electron donating unit, and here you can recognize the perylenediimide unit. So this is actually 3 times the same molecule, but with different orbitals. Now, in between these two chromophores, they have positioned a folder, which is like a helical bridge unit. A helical bridge unit consisting of quinoline moieties. So, from the fast spectroscopy, as well as the molecular orbital calculations, we have very strong indications that the folder unit, that it acts as a very good mediator for the electronic coupling, which is of course very important in the charge separation. So you see that the HOMO of the system is only mobilized on the OPV unit, on the oligo-phenylene unit. The LUMO of the system is only localized on the perylene unit. Here's the molecular structure, here's the orbital. Now, the orbital that is involved in local excitation and in charge separation, you see that it is delocalized over the folder units. So this is a visualization of the electronic coupling through the folder units. And this brings me to thanking these people and leaving you with my molecular system. Thank you. That's it.
So we can have a few questions, if you have any questions to Dr. Williams.
Thank you for a nice talk. So my first question C60. So, what kind of method did you apply for this? Collection of two molecules.
Yeah, of course, there are various methods to functionalize C60. One is the 1-3 dipole addition, the proton methods, asymmetric. You can do Diels-Owen type reactions.
Especially, so I would like to know if you use also manganese triacetate. It's malonic esters and C60 together, putting the manganese triacetate and the plastic. If it does work, you really use manganese.
So, okay. The first step, you mean the big addition?
No, connection of the malonic ester part with the C60.
Yeah, so that is Bingel type conditions. So you use DBU and iodine in toluene. It's the Bingel reaction or the Bingel adduct. Actually, it's commercially available. The compound, which is like this, you can nowadays buy it at Eldridge.
Oh, it's commercially available.
Yeah.
So I talk about there are some Chinese, we are using manganese triacetate. So it's also interesting.
For Bingel addition type reactions.
No, the addition of the malonic esters to some hydrocarbons.
Yeah. No, we didn't use that. This is, okay, Bingel published this with DBU and iodine in toluene.
So second short question is, what's happening if you if you have restricted structure of this compound by using this connection part as a double bond and triple bond? So with the nitrogen and oxygen.
That is an option. We have not investigated that, but we are thinking about using just a fixed, like a 5-member saturated ring, because you want to have the energy transfer to be as fast as possible, and we see that that's actually in the stacked conformation. So if you can get these chromophores just to have pi contact, that actually works the best, and that is basically this conformation. So this conformation works very well. So if you just take the spacer and actually make a 5-member ring here, then you could fix this pi-stacked conformation. I think introducing double bonds or triple bonds will make the distance longer, and that has a large influence on the rate of energy transfer. And so this side is basically an image function that is still free. So I was thinking about introducing, some supramolecular units so that we can make nanoscopic interpenetrating networks with this compound.
Thank you.
Here.
Okay, another question. We thank Dr. Williams for his interesting work and nice presentation.